The objective of this demonstration is to develop a relationship between the step size in numerical differentiation with the error computed from the analytical expression. So we have a function here f of x sine of x whose analytical derivative can be computed at any point x as cosine of x. So here I have chosen the point pi by 4 and its derivative is cosine of this number pi by 4. It is 0.7071. Here is the numerical derivative approximation uh, from the midpoint formula. So I will take several h values, so step size values, and this will be the numerical derivative, numerical df, and here I will compute error. So let's take several values. For example, 1 e raised to the power minus 4, then 5 e raised to the power minus 3, then 2 e raised to the power minus 3, then 1 e raised to the power minus 3, then okay, 5 e raised to the power minus 2, then 2 e raised to the power minus 2, then is 0.001. Well, it should be 0.01. Okay, and I can go for further larger step sizes. This is not the right way, so I keep on writing, then 0.5, 0.2, 0.1. So these are the h values. Now I compute the derivative approximation. So it will be equal to f of x. So I have to compute sine of x plus h. So I can pick up x value from C $1. So it has been highlighted and picked from the respective cell plus the h value B4. This is equivalent to computing f of x I plus 1 minus sine of again C $1. It is from the cell minus h value from its respective cell and divided by 2 times h, 2 times the h value. It's the midpoint formula. So we have got a value. Then let's compute its error from the exact value. So I write absolute function, the approximation minus the true value, analytical value, and absolute error of these two. Then I will repeat this task for all the step sizes. Up to this point. So it seems that consistently, okay, except for this one, we have an increase in the error. And from the expression, theoretically, it should vary with the second power of h. And also, the total error has a contribution of truncation error and the round off error. So to figure out whether the relationship is exactly h squared, we can plot h and we can plot error versus h. So for this, I select the the graphs, scatter graph, in the select data, add a series, x values. On x-axis, I would like to plot h, and on vertical axis, I would like to plot the error points, error values. Now, the uh, to explore the relationship h squared, um, I will change the both axes to log. We have got our plot. On x-axis we have h, the step size, and on vertical axis we have got error. Uh, Now we can do the regression analysis. This is very handy in Microsoft Excel. Just make a click on the data points, the right one, the right click, and here add a trend line. It offers several um, relationship relationships based on the um, regression analysis. So, for example, the linear has been selected by default, and we can set the intercept to 0, and we can display equation on chart. And to see how nice it is, we can um, we can set the parameter, the r squared value, and if r squared value is close to 1, which means it's a reasonable approximation to for the data. So for this model, since we were looking for a relationship h squared, so I can change it to a polynomial, my regression model uh, of order 2, and I set the option set intercept to 0. Therefore, the intercept, the constant in the expression has been removed, has been eliminated. Now equation on the chart and r squared value. So it seems it's a perfect model um, for the data and for our experiment. It means the error varies with the h squared value. This can also be seen if we change the axes to logarithmic. So I select the option from here, logarithmic scale. Similarly, I have to change the vertical axis to logarithmic, and then let me ask Microsoft Excel to give me a relationship in the form of a power relationship. So we have got this equation displayed here, which says that the error, the vertical axis error, varies with the almost second power of h, the step size. Now to see the effect of round off errors, let me select a very small step size, and my objective is to show that this relationship is going to be disturbed, this exponent is going to be disturbed as I choose a very small step size. So for this one, I change here e raised to the power minus 10, and the next value I change 10 times of it, and successively uh, I change the values of the step size, and Here you can see the step size is on the order of 10 is power minus 10, then 10 is power minus 9. So it is nanoscale. This is the micro scale, this is milliscale, and this is the centiscale. So if we now see the expression, so the data points, we can see that with the very small step size, the error tend to increase. And this is evident also in the exponent, that the exponent has been reduced from almost 2 to 0.3567. So that is the effect of it is the effect due to the uh, round off errors. So the round off errors dominate when we use very small step size. So there is always an optimum point for the step size, so that we have the reasonable approximations with respect to the round off errors control and the truncation error control.